everyone. My name is Adam and I'll be teaching you all about strength of materials. This is specifically the English version of the strength of materials series that I've already published 2 to 3 videos in Hindi. So this is the English language version of the same. Okay, strength of materials is the study of deformable bodies. Okay, as you can see here, a deformable body is the one which deforms under the application of forces. Right? A body can deform in both ways. A body can compress, a body can elongate, right? Depending on in which direction the force is being applied. So in this first case, the force is being applied in a compressive manner, right? So it results in a compressive deformation, a decrease in the longitudinal dimension of this bar. Right? In the second case, the bar is acted upon by an axial tensile force which causes the bar to elongate by a del L amount, right? Okay, so strength of materials is basically the study of these kind of deformable bodies. Moving ahead, we'll be learning about stress and strain. So, a stress is resulted due to is a result of the internal resistance that is produced due to the external force applied on the body. Here you can see a force F is being applied on this bar. This force F causes an internal resistance to be produced inside the body, which tries to resist this force, resist the application of this force. Okay, so this internal resistance per unit area is known as stress. Okay, so this internal resistance per unit area is known as stress. Right. Let us quantify it for a circular dimension rod. So here you can see a circular cross-sectional rod. Okay, so this rod is of diameter d, so its area can be given as pi d squared by 4. Now the stress can be quantified as the force applied divided by the cross-sectional area. That comes out to be 4f by pi d squared. So here you can see that we are taking the applied force to be equal to the internal resistance. So one thing to be noted is that in strength of materials, in almost all the applications that we'll be studying in this subject, the internal resistance is taken to be equal to the applied force. Okay. So internal resistance per unit area can be approximated as F by A, the external force applied divided by the cross-sectional area. Okay, so this is stress. Now, stress can be classified into 3 types basically. Normal stress, the first one is normal stress. Okay, let's start with the normal stress. So, normal stress is the one in which the force acts perpendicular to the cross-sectional area. So this is the cross-sectional area right here. Let me draw it in 3D so that you can have a better view of it. This body, this is the area. Sorry, this is the area. So, pardon me. This is the area which is acted upon by F. So this area is the cross-sectional area A, right? So the force that is applied on the object is perpendicular to the cross-sectional area. This is why the stress produced due to this kind of application is known as normal stress. And normal stress can be further classified into compressive and tensile stress, as we have already discussed uh, in previously here, that compression means a force that causes the body to be compressed. In that case, the stress is known as compressive stress, and the stress which causes the body to elongate is known as tensile stress. Okay. Now moving ahead, now we'll be here. You can see that a body
body object right here, the A, B, C, D, is being acted upon by a force which is tangential. This force is tangential to area, this area, right? This area, uh, like this. This area is here. This force is tangential to this area A. Okay. Now, this force will cause the body to deform like this, as shown by the red dotted line. This body will deform like this by an angle phi. This is known as shear deformation. Okay, shear deformation, and the stress acting here is known as shear stress or the tangential stress. Okay, the shear deformation can be quantified as tan phi equals to d by h, and when phi is very small, you know that tan phi can be approximated as phi. Okay, so phi is d by h. D is the deformation, shear deformation right here, right? Not the shear deformation exactly, the deformation in the size of this AB shape, you can say. Okay, and h is this dimension AC, then shear deformation phi can be represented at d by h. Okay, okay. Shear stress is F by A, you can see here. Okay, I've explained here as well the tangential area, this tangential shaded area, right? F is tangential to this area. Okay, so this stress is known as tangential stress or the shear stress. Okay, moving ahead, now the third type of stress is volumetric stress. So in case of volumetric stress, the force is applied from all the directions, equal force is applied. F, and F, as you can see in this sphere, all the direction equal force is being applied. This can be very easily compared to an example of a sponge ball. When you hold a sponge ball in your hand, you try to compress it from all the directions equally. The, the sponge ball compresses, right? That compression results in the volumetric stress inside to be developed inside that sponge ball. Okay, so this is known as volumetric stress. Okay, right. So volumetric stress can be approximated as uh, the F by bulk modulus, which I think did not be taught now. Okay, uh, I'll explain this later. Okay, we'll see how we'll calculate volumetric stress when we'll look about in detail about the elastic constants, the bulk modulus, etc. Young's modulus. Now let's talk about strain. What is strain? Strain is defined as change in dimension divided by the original dimension. Okay, so corresponding to the types of stresses that we have, we also have strains. Okay, so for compressive stress, we have compressive strain. So compressive strain can be given by del L by L. Since del L is decreased, del L denotes the decrease in length, decrease in this longitudinal dimension. So this compressive stress is denoted by a negative sign minus del L by L. Okay, okay. This need not be minus ahead. This will come out to be a negative. Okay, so this is negative. Negative. Whatever you obtain is negative. Okay, and tensile strain is whatever you obtain is positive. Okay, del L is positive. Del L by the original dimension turns out to be a positive value, positive strain, and it is denoted by the Greek letter epsilon. Okay, the stress is denoted by sigma. Right? Shear stress is denoted by tau. Okay, fine. Moving ahead. Shear strain. Shear strain, I have already thrown a bit of light on that while explaining the shear stress. So phi is equals to d by h. Okay, so this is known as shear strain, right? Volumetric strain now can be measured by change in volume divided by the original volume. So V by del V by V, V dash minus V by V. The sponge ball when acted upon by equal forces on the sides. Radius decreases to R dash from R, right? So V dash corresponds to the final volume. V corresponds to the initial volume with the radius R. The difference in that is the change in volume divided by the original volume, which gives us the volumetric strain. Okay, so what have we learned till now? Strength of materials is a study of deformable bodies. Stress is expressed as internal resistance per unit area. Internal resistance is approximated as the equal to the applied force, right? We have seen the types of stresses: normal, shear, volumetric. Then strain is change in dimension by original dimension, and we have seen types of strain: normal, shear, and volumetric. I'll be going into detail about the lateral strain in the next video. Till then, keep learning, right? Work hard. Please share, like this video. If you really like this video, please share with your friends, right? And like this video, and please do subscribe to the channel. Thank you.